we go. Can I be quieter? Alright. Okay, I might go back a bit.
Where the memory is, because we don't have any real restriction.
Oh, well, I just started. I think yesterday I got as far as this image thing. Yeah, I jumped ahead quite a bit. Just impatient. I want to see what it looks like, what it does, and then we'll go from there. Makes more sense.
On where it is, we have to say the size, and this is the size of the region in bytes. Basically, if the address parameter is null, the value is rounded up to the. Why is this scrolling? There we go. Rounded up to the next page boundary. So since we did pass in the LP address as null, it means that even if we pass something that is less than even multiple of the page size of the system, it will just round it up for us, which is exactly what we want it to do. So that's totally fine. Then, we have the allocation type, and that is going to tell Windows what we actually want it to do to this memory range. And that the interesting thing about this is there's two actual things it can do. There's commit and reserve. And what's interesting about that is basically, since it is a virtual memory space, what that means is you start off with 64 bits of address space, but basically all of it is essentially vacant. It's not actually memory yet. And you basically have to say, okay, I'm announcing that these pages are actually now going to be used by me, so Windows can know, oh, okay, he's actually going to use some of this memory space. I have to start tracking it and working with it, putting it in physical memory, doing whatever I need to do with it. And it has a little page table basically that it keeps that says which pages for each process are actually being used. Now, what that means is when we go through virtual alloc, there's two ways we can ask for memory. We can ask it to actually start tracking the memory, and we're actually going to start using that memory, that's what commit actually is. But reserve is a separate thing we can do if we just want to make sure that memory is available for us and kind of tell you, okay, we're going to be using this memory, but you don't actually need to start tracking it yet because we don't actually need it yet. So why don't you actually just wait till I actually need it to actually start using it, if that makes any sense. So basically, we're going to use memcommit because we actually want the memory right now. So I'm going to go ahead and do memcommit. And then we can talk a little bit more about that later. Now, I don't think we actually need any of these other ones. We don't need to ask for large page support for any particular reason. We don't need address window extensions or anything like this. These are all things you do not have to worry about, and I don't think we will have to worry about either. And then protection basically says what we want our access privileges to be. Now, we do not need to execute code out of this memory, so we do not need the execute bit to be set. That is basically a bit that says whether or not the CPU can run code that is residing in that memory. This is basically for security purposes, I believe. Well, it could be for forking purposes too. I don't know. Don't get hung up on that. Doesn't really matter. Point being, we want full read and write access. We just don't need execute. So we're going to ask for read and write access to this memory, which means that our process can both look at the contents of that memory and store things to that memory, which we are going to be using both of. So we're going to ask virtualalloc to give that back, and in theory, it will return to us, as you can see from the documentation here, it will return to us a void pointer. Remember, LP, long pointer to void, that is a void star. It is going to return us a void star, which is what we wanted, which is the memory that we needed. Now, if we should have to resize our div section and bitmap memory was already allocated, we want to just make sure that quickly before we do this, we go ahead and free that memory, because that is the only time that we actually want to do that. This memory is supposed to always be available to us, so we only want to free it if we think we're going to allocate it again right away. So basically what we're going to do here is we're going to use the opposite, which is virtual free. What you can do down here in the C also is they'll usually put things that are related, so if you want to know how to free something, you can usually go down here. Sometimes they'll tell you in here as well. Sometimes they won't. Here it is. Virtual free can free the memory. So what we're going to do here is
what's the equivalent of virtual alloc sick? My understanding is with Arena, you don't free it till picked up page allocator. Are the allocations part of a cyclic pattern such as main loop, web server, request handler? At the end of the cycle. Right, okay. So I guess this can be considered as a cycle. And then you're just free. Or fixed buffer allocator. Because we know the size, what we want. Because we know the width, height, and per pixel size, which is 4 bytes, 32 bits. Yeah, we'll see. Okay, I think could be fixed buffer allocator. Yeah, I could try either.
We are going to go ahead and do mem release to actually get rid of the memory entirely. But I'm going to talk about mem decommit just briefly, just to let you know how that works, because we may use that in the future, probably not here, but we will probably use it for other things on occasion. All right, so we are going to free the bitmap memory. We need to pass it the address to free. We need to pass it the size that it was, and that's the bitmap memory size that we allocated before. So it looks like we're going to have to store that, since I assume we cannot pass a null. Oh, no.
Yeah, no worries. I think you're not the first person to think that. The last few days.
We can't actually pass a null. That's good. So it'll actually just free it remembers basically how we allocated, and it will free it.
Like, I think it was yesterday or no, day before. Forgot to have my camera turned on or like visible, I don't know what, on OBS. And someone thought he was talking to Casey. It was quite funny. Yeah, that was an experience.
So that's perfect. So we don't even have to store the actual size. It'll do that for us. And then we just have to say that we want to release the memory back to the operating system, and it can reclaim those pages, use them for something else, give them to another process, do whatever it's going to do. It doesn't have to worry about keeping them back in physical memory on the hard drive anymore. Now, when we do this virtual free, I said...
Hang on. That's the actual memory, and then... Okay.
Mem release, so we get rid of the pages. There's another thing we could have done. We could have done mem decommit. What is mem decommit? Now you notice we did commit over here, which basically said I want you to actually make these actual pages. Release makes them decommit, like stop being committed, but then it actually frees them as well. But instead, we could decommit them, but leave the pages reserved. So if for some reason we said, look, you don't have to pay attention to these anymore, but we're going to actually probably want them back later, so don't bother tracking them, but don't get rid of this memory range. That could be something that we might want to do. Probably not. I don't really know. The thing that we're more likely to do, I'll mention it really quickly, because for some reason I'm spazzing out tonight. I'm just kind of in one of those zones where I'm just talking at you and talking at you and talking at you, and I see no reason to stop. Virtual Protect is a way of basically taking something that we did with virtual alloc and changing the protection of that page. So one thing we could do, instead of freeing the memory, is we could choose to leak this memory in debug mode, meaning we will not free it, it'll just stay around, and instead of freeing it, we will actually virtual protect it. We will virtual protect it with no actual access. So we will go in there and we will change the memory protection memory protection constants of the page to be page no access, no execution, no writing, no reading. So that way we can't use the page anymore, even though it is still allocated. Now, why would we want to do that? The reason we want to do that is to make sure nobody has a stale pointer to the page. Because if someone kept a pointer to the page somewhere and they were going to try to write to it, that would be a use after free bug, which are very hard to track down sometimes. And so this is one way that you can catch those bugs. You can go ahead and protect the memory, make it so that you can't touch it, and then later when that buggy code tries to go and touch it, instead of perhaps succeeding touching it because it's still memory that's allocated by the operating system that got used for something else later, it will now fault right on the line of code that tried to do it. Great way to catch bugs like that. We will probably do something like that in the future to try to keep ourselves from making any mistakes like that. Right now, don't see much of a need to do that. I think we'll probably be okay. There's other tricks you can do with Memory Protect. We'll get into those later. But that's all I want to do right now. I'm going to step through this and make sure that we are doing the right thing. So I'm going to go ahead and type dev-env to bring up our project, and I will step into the Win32 resize dib section. So here we go. Let's make sure that the first time we try to resize our dib section, we expect our bitmap memory to be 0, which it is, which means we will not attempt to free it. That is exactly what we wanted. We will fill out that header. We know that's right. We checked that yesterday. 4 bytes per pixel, which is how many we expected. We will then ask for a certain amount of memory here, bitmap memory size. That is this, which looks about right, 1424 by 729 should be about that. And then when we multiply by the size of the pixel, which is 4, yep, we all good there, looks good. And now we will allocate our memory. And did we get it back? We did get it back, all is good. We are ready to rock. So now all we have to do is pass that memory to stretch.di bits to put it to the display, and that will solve our problem for us. Now what we're gonna do here is I think we're actually going to start. Now remember, we essentially do what's called a dirty rectangle update here. We passed Win32 update window, the region of our window that Windows asks us to repaint. But we could introduce some bugs here and make stuff harder for us to debug by actually using this dirty rectangle first time out. So instead of doing that, I'm going to have stretch.di bits just fill the whole window first. I'm going to have it draw to the whole window first just so we make sure everything is working properly, and then we'll worry about doing a subregion that Windows wants us to do. So instead of doing it this way, I'm going to go ahead and look up that call right there. I figure like this will simplify our debugging a bit. It'll always start simple and then get more complicated. So basically we pass the device context we're painting to, we pass the destination, and so the destination, it's no longer going to be this at all. This is not what it's going to be. So the destination is going to be 0, 0, always, and then we are always going to do our full width and height, the full width and height of the bitmap instead of the repaint region. We're going to pass that, and then we will pass, I guess we should name this, so this is actually the bitmap width and the bitmap height, and then we will use the window width and the window height to make sure that we blit our whole bitmap to the whole window. Now, in order to do that, I need to actually know what size that is. So temporarily, I'm going to go ahead here and I am going to pass the actual window size. It might not actually be temporarily. We may just want to always know this. I think we do. So I am going to ask here for a window rect to be passed in that will tell us basically how big the window is, and then I will save the width and height of our backing buffer here. Again, these are global variables, not because these should actually be global variables, they're because we're just kind of working on getting the code working right now. These will not be global variables eventually. I do not this is not a good thing to leave these global variables, and we won't. So don't be thinking that you should put these things out there permanently. You should only put things as global variables when you're first getting things working and see where everything has to be, and then immediately after you kind of know exactly how things should go, you want to clean that up and make sure that only things that actually should be global are global, and that is what we will do a little bit later. So there we go, we have our global variables, and when we come through
Yeah, I don't think he likes it either. I think it does it more for ease of use initially.
here and we resize things, we are going to go ahead and set the bitmap width equal to the width and the bitmap height equal to the height, and then we will go ahead and set using those from then on. So these will basically just be set there, and then we will just use those from then on. Okay, there we go. So that will be how we'll do that. We then just need to get the...
Hang on, so that's just the window width and height. Yeah, I guess. Okay, that's what he said. It's gonna set it to the window
width, and the window width, of course, is going to be, excuse me, the window rect. Let's see there. I passed a pointer to it because I didn't want to pass the whole rectangle on the stack. Didn't think that was necessary. The window rects, that will be the right minus the left to get us the width of it, and we will do the window height. Will be window rect bottom minus window rect top. There we go. And that should basically give us everything that we need to know. We have our bitmap memory pointer, but the one thing that I do want to know is what order, so stretch to bits, I'm giving it a pointer, but I don't know how it's going to read that pointer. How is it going to access that memory? Is it going to subtract, so how should I say this? So basically it's going to look at that memory and it's going to interpret that memory
Yeah, well, fair.
Is a bunch of pixels, basically, right? And let's go ahead and do a drawing here so I can kind of get across to you. This is a bit of a visual point, and I think it might help to have a diagram. So I'm going to go ahead and draw one using GIMP with my magical drawing skills. I think we all agree that my drawing skills are kind of unparalleled. So let's see. Oh my God! Wow, drawing with OBS is difficult. Oh my Lord. Okay, maybe this won't work. This is why I got to get a video capture card, ladies and gentlemen. That's almost impossible. That's almost impossible to do. All right, so that's a non-starter. There's no way we're going to draw that diagram. I will have to get a video capture card before I can actually draw diagrams. Oh, that's awful. Well, I'm glad we tried, because when it becomes more important, I'm going to need to be able to draw stuff, so we'll skip that for now. Basically, I'll do an ASCII diagram for you. All we're trying to do here is say, well, we've got a 2D thing, right, which is this bitmap, but we have a 1D representation of it, because memory is just a series of bytes. It's a giant series of bytes. So what we need to do is come up with a convention for storing something 2D inside something 3D. So basically, the X, a row of pixels is pretty easy to understand.
Well, I mean, I guess because it's good to draw stuff. Paint.
Because if I just give you a pointer to a byte, you can assume that you just start reading the bytes and they are a row of pixels. But when you get to the end of the row, what happens, right? Do you just store the next row down on the image and then put that there? Do you store the next row up on the image? Do you back up? Do you do some pointer math? What's going to happen there? You need to know what happens at the end of the row where the next row's bits are, because basically you've got a series of 1D slices in memory you've got to reassemble into something 2D. Normally when I do things, I just tack them on. So it's just one row, then the next row, then the next row, then the next row, going usually top down. But we need to know what Windows is going to do.
Well, plus inserting text is a lot easier, I guess, than drawing lines on the screen.
That thing is called a pitch or a stride, typically. The value is basically when you move a pointer, when you're going from row to row, typically something called, I think it's usually called a pitch. The value that you would add to a pointer to the first row to move it to the next row is called the pitch usually. And a stride is the number you would add to a pointer to the end of a row to move it to the next row. I believe that's typically how...
Hang on. I know what he's talking about. Because I do need to. X create image. This specifies the quantum, in other words, started. My feet is itchy. In other words, is it raining outside? Start of one scan line is separated by in the client memory from the start of the next scan line by an integer multiple of this many bits. Ah, yeah, that's 32. So it's going to be like something times 32 will get you to the next line. Bytes per line specifies the number of bytes in the client image between the start of one scan line and the start of the next. So I guess this is what he's talking about. Bytes per line. So that will be width times 4. Let's say bytes. Oh no, so bits time width times 32. If I'm not wrong.
How those two terms are used, but it doesn't matter. Point being, there is some notion of what you do, and we need to know which one of those stretch bit uses. Stretch DI bits uses. So let's take a look at the remarks and see. The origin of a bottom-up div is the lower left corner. So you're talking about something where it starts down in the lower left corner. The origin of a top-down div is the upper left corner. Now, I don't actually know which one those are, but I suspect that it has to do with whether we set the BI height parameter to negative or positive. So I'm going to go ahead and see if I'm right about that guess. Let's take a look. BI height. Let's see. The height of the bitmap in pixels, if BI height is positive, the bitmap...
Hang on, I'll be right back. I need some more coffee. Gotta go back a bit. I missed. I was distracted.
It uses. Stretch DI bits uses. So let's take a look at the remarks and see. The origin of a bottom-up div is the lower left corner. So you're talking about something where it starts down in the lower left corner. The origin of a top-down div is the upper left corner. Now, I don't actually know which one those are, but I suspect that it has to do with whether we set the BI height parameter to negative or positive. So I'm going to go ahead and see if I'm right about that guess. Let's take a look. BI height. Let's see. The height of the bitmap in pixels, if BI height is positive, the bitmap is a bottom-up div. Wow. The brain circuitry is still sort of working. Just barely, folks. Just barely. The bitmap is a bottom-up div, and its origin is in the lower left corner. If BI height is negative, the bitmap is top-down div, and its origin is the upper left corner. So you know what? I prefer top-down. I don't know if it's a performance penalty. We'll see. But we're going to go ahead and say that we're going to make this negative so that we can ask the rows to go sequentially from the top down, because I think that's a little clearer. That's usually the way people expect them to go. And so let's do that for now. That also aligns better with old school programming. Old school frame buffers started at the top and went down. And maybe you could argue that this isn't as good for thinking about new things in 3D where OpenGL wants them going the other way. And you know, we'll take a look at all that stuff later. Don't worry too much about it now. But point being, I'm going to go ahead and do that now just to make things a little bit clearer for people out of the gate. Especially since Windows coordinate system is all top down, right? X is lower left to X starts on the left at 0, goes positive towards the right side of the screen, and Y is 0 at the top and gets bigger when it goes to the bottom. That's a top-down display, so it's kind of weird to flip them around. All right, so back to stretch DI bits. We now know we have a top-down window, so let's see what else it says here. If the parameters differ, they have different signs, we're going to mirror image. We don't want to do that. We're going to use the same signs for top-down image. For div is negative, so that's what we did. The function allows blah, blah, blah. But it doesn't really say what the stride is. It does not seem to say what the stride is here. Does the bitmap info say the stride? I don't think it does. So I guess we are just going to have to experiment, ladies and gentlemen, and see what the stride actually is. So we're going to pass that bitmap memory. We are going to go ahead and see what Windows does. Now, we have not put anything in it yet. So we're, this is something I should note, actually. One of the things that's problematic is basically when you do a compile inside Emacs or from the command line, sometimes MSVC doesn't give you the full path to the file name, and I would like it to give a full path to the file name. So basically when you hit CL, right, if I hit question mark, /question mark, CL/question mark, you can see that it gives me all the compiler options. And one of these options is basically to to get full paths. And so I am going to go ahead and see if I can't get that to happen. I think I've got less installed on this machine. Do I? I do. So I'm going to go ahead and search for full. Let's see, use full path name /fc. Okay, there we go. So fc is what we want in our build.bat. And let's see if I can go ahead and load that up. So let's get a -fc in there, see if that works. And it does. Look at that, full path name. So what's the nice thing about that is now I can just hit return on that in Emacs and it'll jump right to the line, or I can hit Alt-N, which is my go to next error, which makes it a little easier to find these bugs. So we changed the definition of Win32 update window. We certainly did. And so we have to go back and take a look here and call it the correct way. It needs to take the device context. It does. It needs to take a window rec, which we have not passed it. So I'm going to go ahead and take this same code here, this that just got the client rectangle, and I'm going to pass that for now. We may want to clean that up in a little bit, but that should be sufficient. That is the rectangle that we wanted, the same one that we were using to resize our bitmap. So off we go. Let's run the code. We have not put anything in there, so basically we don't crash because we don't know what stretch.di bits is going to do. We want to make sure we're passing it something at least semi-valid. We seem to be. So that is a good start. Now let's go ahead and actually draw those pixels. This is what I wanted to do tonight, and we are already there. I don't know if you can contain your excitement. You probably can't. Did an irritory for a syntax again. Said I wouldn't do it on the stream, and I did. We are going to go row by row through this bitmap, ladies and gentlemen. So we are going to start with a for loop that goes over the bitmap height. And we are going to look at each individual row, and for each individual row, we are going to go ahead and go over each pixel in that row. And for each one of those, did it again. Old habits, hard to break. Using the stream to try and break that habit. I know it's not useful anymore. What can I say? Old dog, new tricks. Sometimes it takes a while. All right. So we have our bitmap memory. It is a big old chunk of memory reserved by Windows for us, specifically for the purpose of writing pixels into it, but we have a problem. It is a void pointer, and a void pointer, as you know, is a pointer to something that C does not understand. So in order to start writing to it, we have to change it into a pointer it does understand. Now what I want to do is I want actual explicit control over the pointer and how it's going to move. So I want to tell C, first of all, basically that it is going to treat it as a pointer to just bytes in memory. So I'm going to cast this to a char star. Now I usually like to use unsigned char star, right? And these get sort of annoying to type. So one thing that we're going to do, and I'm going to start doing it now because why not, is I like to type def some convenient type defs here. Something that's a little easier to type and that means what I actually want it to mean. Because I really don't care about unsigned char. What I care is that this is an unsigned 8-bit integer. So I like to use uint8 for that. And basically, what you used to do in the old days is what I'm typing in right now, right? You used to do bitmap memory, there you go. You used to do that. But recently in C, and I forget exactly where these are defined. I think it's in standard type study. Is that a thing? Let's find out. Is that a thing? No, it is not. Is it in standard lib? I don't know where it is. Who knows where it is? Basically, there are new types that actually have the thing that you actually want, but I don't actually know where they are normally defined anymore. That is not correct, but I know you've got these, so I'm going to go ahead and search for where they are. They only just introduced them recently. Well, recently I'm old, so recently it's probably like 5 years, right? But I always had to do these myself back in the day. Standard int, that's what it is. But they've recently added these, and that's kind of cool. Basically, there are now types which are actually set up to be the correct size for your platform, because platforms used to differ in terms of what sizes things were. So if you said int unsigned, that could have been 16 bits, right? And that's no good if you actually needed the thing to be a precise size. So now that you can actually do that, I'd like to actually do that. These are the types that I used to use, and coincidentally C uses a type which is almost the same, but I like to define
CSTD int.h.
them to be my own way just because I am persnickety that way. You could just
Oh, because it's like, is it because it's referencing the C? No, but C++ you can, right? You can just include C header files. I have no idea.
as well use uint8t. Anyway, that's something to think about. We're going to basically cast this to an unsigned 8-byte integer, and only reason I'm doing that is because I'm going to be doing pointer arithmetic, and as we know from the intro stream, anytime I add or subtract something for a pointer to move it around in memory, C will silently multiply that movement by the size of the thing being pointed to. So if I were to change this to a 16-bit, it would move by 2 every time. And I don't want to do that. I want to make sure I can do the arithmetic explicitly. Now that's just something I tend to do in pixel operations. The reason for that is because sometimes, as you'll see later on, they tend to have strides that aren't necessarily aligned on pixel boundaries for various reasons and stuff like that. It's just a better way to write these loops. You'll have to take my word on it for now. That's just kind of a better way to do it. But once we get in here, we can cast it to what we're actually looking at. And that is a 32-bit integer for going pixel by pixel. So basically what I will do is it's cast my row pointer here to that. And then at the end of each of these iterations, I will increment the row pointer by that pitch, which is the amount we're going to do to move it. And of course, the pitch.
Why is it UN32? Shouldn't it be? I'm a bit confused now. Alright, I'll let it play.
Is the difference between a row and the next row. That is basically just going to be the width times the size of the pixel, right? That is how big each individual row is. A row is width pixels wide, and each one of them is bytes per pixels long, so that's how big it is. So from row to row, that is the size, that is the pitch, and then each.
I guess it's to make sure that the amount of pixel can be supported. It's height. Okay, it's just before he actually writes the row. Maybe. Hang on, I gotta clear my nose. Okay, so a lot of interruptions today, which is fine.
Each row I'm going to access here. Now, again, this is maybe a strange way to write a loop. It's just a good way that I find to write.
UN16 would be 65,000, and that's not enough. I mean, okay. And if I had 4K image, that is way more than 65. Ah, right. Oh, okay, I think I get it. No, I don't get it. Alright, I'll let it play.
Pixel loops, because oftentimes this pitch value, you might say, looking at this, it's totally valid, and you're totally right to look at this and go, hey, wait a second. This pixel, I bet you're just going to do this in there, right? You're going to go ahead and increment this pixel every time, right through the loop to write to the different pixels in the row. By the time you get to the end, it will already be right where this thing is going to be. Why are you doing that? It's inefficient. You're correct. The reason I'm doing it is because typically when we do these things, the pitch is actually not going to line up with this. And so it's usually easier to write them in this way for various reasons most of the time. But the other way we could do it is to just take pixel and add the stride here. 6 and 1/2 dozen of the other. Some may have performance concerns. Those are all things we're going to look at much later, so don't worry about it too much right now. That's just a good way to write those loops, typically before you're going to actually go in and start doing any kind of performance tuning. Now, I went ahead and added UN32 because we hadn't defined that yet. You know what? We
didn't write anything to the pixel itself. Though his loop he's signed in, so he'll never need the mount. Precision, since he can't loop over that many either way. Okay.
Go banana cakes here, folks, and just finish off our typeset entirely and get all the different types that we might use. Well, not all of them, but most of them. Just get them in there. We will be moving these to a platform-independent header at some point because that's pretty good. So there we go. We've kind of defined our various sizes. Good to have on hand. All right, inside here, I'm going to use the dereference operator to write to this pixel. Basically, that says I am trying to access the memory pointed to by this pointer, which should be pointing to each individual pixel, and I need something to write in here. Now, what am I going to write in here? Well,
okay, fair. He's gonna. How CS50 to start programming from scratch? I don't know. I mean, if you've never programmed before, I think can be. Cause it's, I don't know. It didn't really work for me. I tried CS50. You can actually do it after. You can try something else before and then do CS50 after. Because for me it didn't really work. So I don't know about you. Maybe it could work for you. I think a while ago you said you go to the gym, right? Is that a regular occurrence? Not that regular, I'd say. I only go I say this is max 3 times a week. But yeah, I try to keep it 3 because I tend to follow through. And I only squat. I don't do anything else. Yeah, because I don't like all the other workouts. Yeah. So my goal is, it's a bit of a flex, but I'm gonna say it. My goal is to squat 220 kgs. Right now I'm at 170. So that's why I just squat. I like it, and yeah, helps me go to the gym.
each of these pixels is essentially packed in memory. This is the structure of the pixel. Pixel in memory, right? We basically have location 0.
Oh. Yeah, sure. After what? After any of the other open source ones, like Code 3, Boot Dev. Because CS50 does talk about more about the basics. You can try that later. We'll see this in the YouTube chat. Can't see it.
And that's going to be 8 bits. So we basically have in hexadecimal, that is 2 of those things. This is the first one. This is the second one. This is the third one. This is the fourth one. Now the question is, we know we have to write RG and B. Which one do we write it to? And this is the pixel in memory. So this is basically the location 0 from the thing. This is 1 byte in. This is 2 bytes.
Oh, okay. Now I get why it's U32. Because each pixel is 4 bytes. Yeah. So I don't think it's what you were saying. We'll see. Because it's like RGB and then something. I don't know what that something is.
Bytes in. This is 3 bytes in from the pointer. So this is basically pixel plus 0, right? Pixel plus 1, pixel plus 2. Well, they're not really. It's only if that was. It's only if this was a uint8, right? Like I said to that. So this is pixel plus 0 bytes and plus 1 bytes and so on. From that pixel pointer, we are going in memories, right? So this is what that is. Now,
yep. Okay. Yeah. Yeah, it makes sense now.
the question is, which one of those is red? Which one of those is green? Which one of those is blue? Now,
Yeah, this is a good question. Because I think I know in X11, it's the opposite. What's RGB BGR?
if you were going in memory order, you would probably think, well, let's put the 8 bits of red there, let's put the 8 bits of green there, let's put the 8 bits of B there, and let's leave this as the padding byte that you said you were going to have. But what happens if we do that? Well, you know what? I'm just going to do that, and I'm going to let you see what happens. And in fact, you know what I could do? Just to, why confuse the matter? let's just start doing it this way so I can show you full explicitly. Will actually be that way, so we'll just actually do each individual one. We'll basically do the first one, so this will be pixel, and we'll increment it each time. We'll do this. We'll actually do it fully explicitly, right? So we write each byte in memory. Why not?
Why not?
Seems like a good idea, just to show basically what's happening. So let's say we were to write the red first. So, you know, structured art is always a good idea to get things debugged. We want to see if we're writing to this thing properly. So we're going to just write to the red channel, and we'll leave the green and blue channels black for now so that we can isolate the red channel and make sure that we know how to write to it. All right, so we're going to write 0 into what we think is green, what we think is blue, and then what we think is the pad, we'll also leave 0, and then we'll just write the maximum value for an unsigned character, which is 255, into the red channel, or what we think is the red channel. And then we'll compile that and see how it goes. We will now go ahead and run this program. And first of all, we have to see, do we get anything on the screen at all? And you will see we do get something on the screen. But ladies and gentlemen, it is blue.
Because I think it's the same in Windows too. It's the opposite. At least I knew one thing. I'm quite proud.
Why is it blue? Why is it blue? Does anyone know why it's blue? Well, there are experts out there who know why it's blue, but I'm talking about people who took like the Intro to C course. I'm not talking about the grizzled veterans. You know why it's blue.
I didn't know why it's blue.
It's tricky. But we did cover it in the Intro to C course. We did cover it. The reason is because this is a little endian architecture, ladies and gentlemen, which means, as I specified in the intro stream,
I didn't know that.
when bytes are loaded out of memory to form a bigger value. So if I wanted to load 4 bytes and produce a uint32 out of them, the processor will actually put the first byte in the lowest part of those 32 bits. The second byte will go in the next part, and then the next part, and the highest will be the fourth byte over. So basically what happens is if these are the pixels in memory, if you were to load them into a uint32, you would load them R first into the low. I'm going to use the hexadecimal notation we learned. Here is our 32-bit value in a register. 32 bits now, it's one big value, right? The first 2 R and R go down here. The next 2 GG go in here. The next 2 BB go in here. The next 2 XX go right there. And look at that. It is backwards now, BGR. Well, the people who wrote Windows didn't like that very much. They were on a little endian architecture, and when they loaded a 32-bit value and thought of it as a pixel, they wanted it to look like it was in the right order when they were looking at it in the register of the CPU. So what they did is they defined the memory order to be backwards. So it would look like that, which means that it is swapped in the memory of the machine. So all Windows bitmaps actually have the blue byte first, the green byte next, the red byte after that, and then the pad at the end. That is basically how that works. And, well, there's really no other explanation for it than that. So what that means is if we actually want our red to show up as red, we need to move it to the third byte, and then we run it, and now we've got a red bitmap, ladies and gentlemen. Isn't that beautiful? And I argue that it is, in fact, beautiful, a very beautiful thing. Now, what we might want to do is start to make this a little bit prettier as we go. Let's see if we can do something a little bit cooler. How about we go ahead and assign just the X coordinate, casted down, so truncated basically, chopped off, if you will. Just take the lower bits of that value, and we'll go ahead and assign green into the Y channel. And then I don't know what we'll assign to blue. I guess we'll just leave blue black. Or sorry, even I'm messed up now. This is actually blue, not red. So this is the red channel. That will be empty. So this way we can at least get a little amusing gradient going on. There you go. As you can see, much more attractive than what we were drawing before, if still not a game. At least something kind of fun. And it looks like it is all working correctly. And now you can see what I did there, pretty straightforward. I just said whatever our X position is, I'm going to take the low bits of that, and I'm going to shove it directly into the blue channel. I'm going to take the low bits of the Y, the row that we're on, shove that in, and so you basically get exactly that look. You get 256 pixels of increasing blue, and then it drops back to 0. 256 more of increasing blue, drops back down to 0, because that is just the 8 bits of the Y value going up and up and up. I hope that is pretty clear to people what's going on there. Won't belabor that point, but we can go over it in the Q&A if it is somehow mysterious to you. Now, ladies and gentlemen, we have done something that is rather remarkable, if you will. we have gotten ourselves back to 1980. That is what we have done. I could not be happier. But what just happened right before your very eyes is we have turned this modern...
No, I don't watch the Q&A, but it'll be too long otherwise.
awesome, beastly computer running a hugely complicated and difficult to wield operating system into something where we just basically have a bitmap that we can draw to and get back to the joy of coding, because there is no stopping us now. We can draw anything we want to that. But there is something we could still do. We have 20 minutes left in the stream, and 20 minutes is just...
Okay, I'm gonna try to do that much. I am close. Gonna get rid of this buffer. And then, where do I use white pixel? Change this to black. Okay, resize window. Where did I use the buffer? Okay, right here. Maybe call this redraw. Then yeah, draw if it's resize. I can get rid of this. Gonna do that now. I usually use the LSP, but it didn't work this time. Let me restart the LSP. Okay, now it's working. Go ahead, let me see. I can show you an easier way. Okay, now that my LSP is working, I think that could work. I'm gonna undo that and that. So if I go, whoa, sorry, I pressed pressed the wrong one. Can I just make it null for now? Hang on. Okay, for some reason, let me just quit. My LSP is not working. Yeah, I'll show you. Fucking size. How do I just ignore this for now? Okay, there's no more errors. So you go to the definition, and you go rename, and you see on the bottom shows like new name, and I go redraw, and then save. That's it. So it changes it wherever it was defined. It's easier. And how that works is config slower, no, LSP Rename. Alright, it usually works. I always have the LSP. And the star one, yeah, okay, I see what you mean. Stopped using LSP anyway. Okay, fair enough. But I like the LSP. Right, okay, to redraw. Need the size. Fuck, did I just undo it? No. Okay. Get rid of this. I can get rid of that. Need documentation, fix buffer, allocator. They have an example. Okay, I defined the buffer ahead. Going to be... I need the size back. Yeah. Times... Oh, cheers. Sounds cuss. Okay, so this is... should be 4. 8 times 4. No, just 4. Size. But again, it's not comp time known, so it might not work. Well, let me try. Pretty sure it's not gonna work. And standard dirt. Keep. Dirt in it. FBA dot allocate. Oh, you get the allocator. Guess I don't need buffer anymore. Sorry, data. Excuse me. So I can replace buffer. Might need to cast it. I mean, if it doesn't work, I just change it to an arena. Is it an array? It is. We need to go to wa dot height. Yep. So the question is, the buffer is actually U8. It's a byte. Something doesn't look right there. I think there should be 32. Height times width times 4. No, then I'm a bit confused. Let me rename that to pixels. Actually, in that case, size would just be height times width. Oh no, because we gotta change it to a... Man, I'm not gonna lie, I'm quite confused. What do I do with the allocator? Wait, do I even need? I don't know yet. I think I don't really need. Do I need that? Yeah, I can use it to write the pixel. Let's say I have a 2x2 screen. So I'd need SD, RGB and padding. And then that would be the same. Which would then be written that way after. Digging the line completion mode. What is that? Hey bossy, you've done this before. What am I missing here? I feel something is wrong. Fair. Well, I'm trying to write to the pixel. But pixel is like, pixels are single dimension, right? That's why I had to do something with the row thing. Oh, let me just check what case it is. But they're already like 32-bit. So I could just write a once. What is this? Row plus equals pitch. Width times byte per pixel. Oh, and then he passes the row later. That one's easy because I can just do pixel width multiplied by the width. What is pixel? It's a uint8 pointer. Oh, it's a slice or an array. Equal to uint8 pointer row. So he's casting it. Oh, okay, that makes sense. Okay, now I understand. So for each element in the row, I gotta write a pixel. This one, I think I don't need the 4. I'll figure that out later. And then here, I can write pixel. Okay, now I understand. I'll call it pixel index. Much easier. Pixel index plus equals, what's this? I. Let's call it y. And then this will be x plus equals y. Don't need that right now. Oh, no. I think it's better to call it. Let's call it row. X will be row plus x equals. So that's blue, and then black the rest. Green, BGR, and then the padding. I don't know, that looks kind of right. I haven't allocated. Then the next time it comes here, I'll make it global either. Oh, cheers, Bossy. I don't have any alerts turned on. Hey, Lucas Develops, thank you for the raid. I should really get my thing is here, stream manager. Okay, I see it now. Thanks for letting me know. I have no idea otherwise. Oh jeez. You came at, well, I don't know. It's a good time. I'm kind of like confused with the whole thing at the moment. Clear all pixels. Oh no, not clear. Very old pixels buffer. And then I gotta change it to set it to 0. I can't really use I can't leave it outside because oh, this is quite the challenge. What is ECS? Entity Component System. Is that it? I don't know why I said that. I've heard it somewhere. Surprised myself that I knew it. Okay, I'm gonna change this to an arena allocator. I think it makes more sense. But always forget. Hey Taras. Standard dirt. Arena allocate. Arena. Net. Heap the page allocator. And then, yeah, okay, this one. How do I get the allocator again? Then when I resize, I can redraw. Allocator, standard dirt, mem. Yep. And where do I use redraw? Okay, so I guess here. Can I even do that? Slice of view 8 equals defined. Get rid of that, get rid of that, and that. If pixels not equals. Hang on, can I just call it? Could be null. Created of free pixels. Is that correct? Oh, I think that makes more sense. Just reset. Makes it easier. This can just be go back. Undefined. And I can use an edit list. Get. Where's init? List dot init allocator. Okay, that makes sense. Oh, hang on. I didn't specify the type. U32. That's done. Ooh, that's a good question. Do I need the size anymore? Not really. Think for later. And then here, dot items. I don't know. I don't know if this is gonna work. And X create image. Bytes per line. Bytes per line is 32 times bytes per line. Okay, I'll use this. Bytes per line is width times 4. Let's see what happens. Standard has no right. Keep dot arena. Set again, found const. D init. What's it called? Is that a typo? D init. Reset. So what is it called? Mem.. Oh, I need the see what it means. Because I think allocator does not. Create, destroy. Pointer. Because I think it's arena dot reset. Yep. What's reset mode? So what does that mean? So preheat the arena for future allocations. Releases all allocated memory. Yeah, I think free all. What's the difference between destroy and free? Free and array allocated bit. Free a single item, C destroy. I have to say, in this instance, the C one looks much simpler. Okay, let me just pass. Don't really want to. Hang on, why do I pass the allocator? Let's pass arena. And keep dot arena. Don't need this. Okay. Okay. And then I can no cleaner. I think it's just me. I am quite new to Zig, so I think it's more a me problem than the language problem. Okay, I think that should work. Well, I say that. Oh yeah, I forgot about. What does it need? Reset mode. I think it was a union. Dot free. Oh. Yeah, I guess. Expected type, blah blah blah. Mount const. Fuck, cause it's a parameter. Okay, I mean. Yeah, just pass pointer. Where's redraw? Why can you not? Oh, sorry. My bad. My bad. Okay, perfect. I'll just ignore it for now. Handle memory reset problems. Expected type usize found scient. It's easy to fix. I guess it's gonna be the same problem. Yeah. Yep. Think this is no longer necessary. It is. You know, it's pissing me off. I just want to smash the keyboard. Okay, let me just take a sip of coffee, calm the fuck down, and then do it. Return the. It's not helping. Not helping at all. Um. So what I need is a fixed size array, which is com time known. Well, unknown, because only when once the window is up and running can it be usable. And then yeah, I think this doesn't make sense. Mhm. Allocate. Okay, there we go. Why don't I just use that? Get rid of that. Yep, pixels. Pixels is going to be hater dot alloc u32 and then size. Now I can use size. And if you catch an error, unreachable. Okay, that sounds about right. Get a slice of U32. Okay. Okay. Perfect. Pixels dot items. I swear it's not gonna work because the X window system, the data is a char star. That means slice of, it needs to be slice of bytes. U8. And let's run it. Yeah. I knew it. That's a bit of a problem. Does that mean I need to okay, I get it. That's why I had times 4. Actually, I should use const. Is it bytes per pixel? Okay. Means this needs to be 8. So every time I write, I need to write 4 pixel values. RGB and the padding. Means I also need to keep track of the index. Hang on, I don't need that. Plus 0. Is that correct? Yeah. 1, 2, 3. And this will be, it's a byte, so this will be blue, green, okay, now I just gotta fix the pointer. Think I know how to do that. I am not sure. I can I do a pointer? No way. It actually worked. But now the moment is truth. Okay, I mean, it's not blue, but something's happened. Okay. But I don't know what is happening, but something is happening. I want to check resize. Resize request and the debug.print. Window resized. It's event dot something something dot x resize window resize request dot, yeah, and then event dot x resize request dot height. And the height first. Okay. Also update buffer size. No, don't need to. It's definitely the redraw. That's not correct. And it debug.print window attribute. Should be the same. Height, comma, width. Okay, it's off by a little bit, but it is correct. Whoa, it's not. Okay, that's good to know. I think that's the first thing I need to fix. So that would be updated. Is it the original 480 by 600? Yeah, it is. X window. There's only one thing. Okay, this is not ideal, but gonna do. And then okay. Then dot x resize request dot height. Then okay, for now I'll just use the global. I can pass it in the argument later. No, what am I doing? I don't need this. Hang on, I can remove this cast. Fix that. See, you went. Where's that? 68. Yep. This is the biggest challenge. Working with the library in Zig. It's all the fucking casting. But once we have the window going, don't have to do this anymore. It's only the first bit. Bytes per line, sure. Hey, how come that wasn't a problem? Oh, okay, because I use width. My bad. And cast. Okay, so at least everything should be gray or white. Why the fuck is this just this bit gray? Whoa, I just broke. What did I break? Transitive failure. Turn image. Root domain. I mean, that's a problem for. Oh, okay. Cast causes pointed to be null. Okay, that's a problem for later. What is data? X create image. Specify. Okay, that's brilliant. function allocates memory needed for an X image structure. Hang on. If it allocates memory, why have I been fucking around with the allocator for so long? But does not allocate space for the image itself. Huh. So I've been allocating the wrong thing. Allocates the memory needed for an X image structure for the specified display, but does not allocate space for the image itself. Interesting. So I guess in where's the image? How can I allocate a C pointer in Zig? It's a good question, really. C pointers. When a C pointer is pointing to a single struct, dereference the C pointer to access the struct's field or member's data. Well, this might be a small problem, really. A tiny one. Where I might have to switch to see. I mean, I guess this should be possible. I don't know the type. Allocator dot alloc. Can I do any opaque? I don't know the size. Oh yeah, is that a size of? No. Oh, but it'll just save the pointer size. Hang on, I gotta ask Cloud. Can I allocate a C pointer to a struct in Zig? Okay, at least it says you can. Allocator dot create. Okay. I don't need to know the type. Oh. That's not gonna work, is it? Allocator dot create. I mean, if I'm using C to allocate it, yeah, that's what I was thinking. Use any opaque. Oh, that's actually a good idea. I use an external struct. C dot X image. What does it return? Error type. Which table? Okay. Now the question is, nah, didn't work. Where's the doc? Rather initialize the structure byte header, blah blah blah, and returns pointer to an X image structure. The red, green, and blue mask values are defined for Z format images only. D3, D12 copy operations is annoying. What do you mean? And derived from visual structure passed in. Other values also are passed in. The offset permits the rapid displaying of the image. Okay, that makes sense. The offset permits the rapid displaying of the image without requiring each scan line to be shifted into position. Okay. So I can just pass 0. It is contiguous. Okay, something's happening. At least I can see the lines moving. It's not printing to the whole. Can't see the edges. Okay. That's not what I expect to happen, but something is happening. Contiguous memory calculates the value of bytes per line itself. Okay, perfect. What is X add pixel? Takes an image value. Function adds a constant value to every pixel in an image. Ooh, I feel like I'm so close. What am I missing? Let me just check. Cons. Should be the same, really. But doesn't hurt to check. comma width. Okay, that's not very useful. Whoa, that one was different. I think I might need the debugger. Where's handmade? Elemental PQRs. Set it here. Can I see? Where did my window go? I lost it. Watch. Image. Done. Pixels, maybe. Oh, but I need the window to resize. I think if I turn off tiling, should be able to see both. That's weird. Data doesn't look right at all. The size doesn't look right either. Whoa. Go back to redraw. 1158248. The size looks wrong. Is there a calculator in here? Window attribute never changes, so that's not very useful. Pixels also doesn't look correct. That looks wrong. Ah, fuck. I know why. That's kind of stupid. But even then, should all be white. There shouldn't be any black on the screen. Get rid of this for now. And that. What's happening to the rest? That's weird. Debug. Spending. Where's spending? Yeah. And redraw. This might break the CPU. Oh, I missed. There. So it's the resize that doesn't work, which is fine. That can be fixed after. What's with the pixels? Continue. Why is it like gray and white? If it was all white, it would have been fine. I don't get it. I think I'm missing something. Clearly. Alright, I'll figure that out tomorrow. But I think once I figure that out, the rest should be a lot easier because I don't need to wrestle with X11 after. So this is like kind of the biggest hurdle at the moment. The rest is just programming. Hopefully. Well, we gotta be optimistic. Alright, thank you for hanging out. I would have liked to have some colors come up on the screen today, but didn't work out. But yeah, have a good rest of the day. You too. Take care, Bossy. And then I shall see you back here tomorrow.